Hello and welcome to this episode. Because this video is about practical hands-on implementation of something similar to the gradient descent algorithm that I described in the previous videos, I assume that you have already watched the two videos on gradient descent where I gave theoretical explanations and intuitions as to how the gradient descent algorithm works. Also, because I haven't shown you how to evaluate partial derivatives, I am going to choose a simple problem set which involves only one weight parameter to be learned. And because there is only one weight parameter to be learned, we can get to the correct value for the weight parameter through trial and error instead of using derivatives. And so in subsequent videos, when I show you how to evaluate partial derivatives, then we can have the proper implementation of gradient descent algorithms using actual neural networks. Okay, so what we are going to do is I have already imported NumPy and Matplotlib. NumPy because we do vectorized computations, and Matplotlib because we want to plot our cost against the epochs. So we basically want to plot our learning curve to confirm that our implementation of gradient descent through trial and error indeed works and converges to the correct value that we expect. Okay, so I'm going to generate numbers between -50 and 50, and I'm going to use the NumPy linspace function. So np.linspace, I'm going to generate between -50 and 50. And I am going to create another vector y which is related to the vector x by just multiplying everything in x by 0.45. Okay, so if we plot this, we expect to see a straight line because everything in y is just an item in x multiplied by 0.45. So it is basically scaling the values of x to come up with the values of y. We can confirm that by plotting. So I will say plt dot, I can make a scatter plot of the x and y values, and let's see how it looks like. So you can see that indeed on the x-axis are the x values, and on the y-axis are the y values, and it is indeed a linear relationship between the two vectors. Okay, so 0.45 is the parameter. This is an artificial data set that we have generated, so we know how x and y are related. We know the relationship is y is equal to 0.45 times x. But for the sake of learning, we are going to assume that we don't know the multiplicative scale factor that we use to generate y from x. Indeed, we know that it is 0.45, but we are going to write an implementation of gradient descent using trial and error to come up with a value that should be close enough to 0.45. And indeed, we will prove that gradient descent actually works and is able to come up with a value that is close enough to what is on the ground truth. Okay, so what we are going to do is, because I want you to have reproducible results that are similar to mine, I'm going to seed my random number generator to 1. So if you want to get similar answer to what I will get, you need to seed your random number generator to 1, because we will be initializing our weight randomly, and if you don't seed it exactly as mine, you will start off with a different random number, and your answer, even though it will be very close to 0.45, is not going to be exactly what I get. Okay, so we are going to assume that the relationship between x and y is linear, and we can get that by just multiplying x by some multiplicative scale we call w. And because we don't know it, we are going to assume a random number. So I'll say w is equal to np.random.rand, and I'm going to generate just one random number. So it's going to be a number between 0 and 1 that is chosen randomly. Okay, and we'll also create a variable called step, which is very similar to, it's going to serve the purpose of the learning rate that I spoke about in the previous videos. Okay, and so I'm going to set it to 0.0001. And we're also going to choose the number of iterations. Here I call it epochs, and I'm going to set that to 5,000. Once again, we don't know if by the 5000th epoch, our implementation of gradient descent would have converged and we'll be able to come up with the correct value that we expect. But like I explained previously, I said there is no science when it comes to choosing the number of epochs. It is very dependent on the problem you're trying to solve, and so you have to try something. If it doesn't work, you either increase or decrease it depending on what you are observing, and that is why it's good to plot your learning curve. Okay, what more do we want to do? We want to keep track of the cost that we incur as gradient descent progresses, and the expectation here is that the cost should be reducing as the number of epochs increases. Okay, so what we are going to do is we loop for epoch number of times. So for E in range epochs, okay, we will use the randomly initialized W to come up with our predictions of Y. And so we say Y hat, which is our predicted Y values, is equal to X times W. Okay. Now, the next thing we want to do is we want to evaluate the cost that is incurred. The cost is basically a reflection of how wrong the gradient descent algorithm is because of the current value of W. Okay, so you say cost is equal to np.mean, and then you evaluate Y hat minus Y, and then you square it. So in the previous video, I explained that one of the cost functions that we use is the root mean squared error. This is it. Let me type it here. So root mean squared error, okay? And how you calculate that is you subtract the ground truth values from the predicted values, and then you square it. You square it because you are not interested in knowing whether you are wrong in the negative or positive direction. You just want to know by how much you are wrong, okay? And then we calculate the mean because we are doing this over vectors, a vector of numbers. So Y hat is a vector and Y itself is a vector. Okay, so after this point, we would need to evaluate partial derivatives. Unfortunately, I haven't shown you how to evaluate partial derivatives yet, and that is why I have intentionally chosen this very simple problem set where we can simulate the calculation of partial derivative by doing trial and error. Okay, so what we're going to do from this point on is we will bump up the value of W by adding the learning rate to it. So if at this point our W is 1, we will just add 0.0001 to it to become 1.0001, and we will use it to perform this same calculation, and then we evaluate the cost. The whole idea is we want to see if our cost increases when we bump up the value of W, or does it increase when we rather bump it down. When we finish, we compare these two costs with the actual cost that we have, and then we will see which direction we want to take. Okay, so what we're going to do here is I'm going to say cost up, which represents the cost when we bump up our W. And so I'm going to do np.mean, okay, np.mean, and I'm going to evaluate x times W plus step, okay, and then I'm going to subtract Y from it, and then I'm going to square it. So this is basically multiplying, is the same as how we came up with the Y hat here. We are just multiplying X by the current value of W increased by step, and we want to take little steps because we want to figure out the value that is close enough to what we expect to see, 0.45, and because we are not sure how we'll get there, we want to take baby steps, and that is why the learning rate has been set to 0.0001. Feel free to play around with different values and form your own intuitions as you perform your experiment through this coding exercise. Okay, so the next thing that I'm going to do is I am going to evaluate the cost when we bump down. So to bump down, you just subtract step from the current value of W, okay? And what we do is, because we know the cost at the current value of W, we have already evaluated this cost using the current value of W, because Y hat is calculated using X times W. And so we're going to append that to our cost list, cost.append cost. Okay, now this is the point where we want to see which action takes us downhill. Is it the bumping up or is it the bumping down? And the way we do that is we would check if cost up. So if the cost we incur for bumping up the weight parameter is less than the cost incurred for bumping down. Sorry, I need to call this down. So if the cost up is less than the cost incurred for bumping down, then what we want to do is we say weight is equal to weight plus step. And then we check if the cost down is rather less than the cost up. Then what we want to do is we want to say weight is equal to weight minus step. Okay, so I explained to you that this is the point where calculus will really come in handy. And the reason why it is important to have calculus here is it is automatically going to help you evaluate partial derivatives, and we don't have to do this trial and error. But because I haven't shown you how to evaluate partial derivatives, that is why we have to take this trial and error approach. So the point here is you have evaluated your Y hat, which is your prediction of the Y values. Now we compare the predictions to the actual values, we subtract, and then we evaluate the cost that we are incurring for the current value of our W. The next thing we do is we bump up the value of W by increasing it by step. We just add step, which is a very small number, to the current value of W, and then we evaluate the cost again. Over here, we evaluate the cost when we bump it down. That is why we are doing the subtraction here. And then we append the current cost to the cost list. This point, we are checking if bumping up results in a cost that is smaller than bumping down, then we want to increase our W, because if you want to bump up, you actually increase the value of W. Mind you, over here we are not storing W plus step into W. We are just evaluating it to see if it is going to increase our cost or is going to decrease it. So if we are sure that increasing our cost is what gives us a smaller cost, then we want to increase our weight matrix. Our weight parameter. And if bumping down is what takes us downhill, then we want to decrease our weight. Okay, so let's run this cell, and then okay, now this cell has run. How do we know we were correct or wrong? Mind you, the value we are after should be something very close to 0.45. So at this point, what is storing this value we are after is our weight parameter here. So let's print out weight and see what we get. So we print weight, and let's see. So you can see that weight is equal to 0.450022. So that is actually not too far off from 0.45, and that is how gradient descent in neural networks actually work. You will not get the exact value, but you get as close as possible. Okay, so if you have a data set and the relationship between your X and Y is 0.45, and you are able to use gradient descent, this very rough implementation of gradient descent, to figure out the relationship to be 0.45002, I mean, that is a great start. That is good enough. So the next thing we can do is to actually plot our cost to see how our cost drops as the epoch increases. So to do that, we're just going to do plt.plot, and I'm going to just plot the cost list over here. So this tells us that our algorithm converged almost before even the 1000th epoch. It converged around something close to 500. So I can assume it is maybe 300. Let's try that and see if it is true. So I'm going to change this to 500 instead of 5000 so that we don't run for that long. So we evaluate our rough implementation of gradient descent again. Let's check the value we are getting, and indeed we are getting 0.45002, and then we plot, and you see that getting close to the, I mean, it converges even before the 400. So right after 300, it begins to figure out the correct value for our W. Okay, so feel free to play around with this code, play around with the step value. I mean, you can change it to, let's say, 100. And the whole idea is to serve as an exercise that will help you to form your own intuitions about what you have learned so far. So you can see that when I change the step size to 100, it gets to 0.412. I want you to try to figure out why is it so. Play around with different figures over here. Play around with different epochs. Play around with different step size, and then try to get the intuition. It is very, very important that you understand how this thing works. So like I said at the start of the video, this is not the actual implementation of gradient descent, because I haven't shown you how to evaluate partial derivatives. That is why we are doing a true trial and error. So if we knew how to evaluate partial derivatives yet, then there's no need for these trial and error calculations over here. But for the sake of understanding, we had to do this so you appreciate that gradient descent indeed works and is able to figure out every relationship that exists between two or more numbers. Okay, so thank you very much for watching, and I'll see you in the next video.